All right, reaction video number 13. I got the number wrong yesterday. I didn't get to say 12, which is one of my favorite numbers because it's the largest integer with one syllable. But anyways, we're up to 13 now, unlucky 13. And I think this one is going to be about momentum. So let's go full screen on it. There we go. And let's get started.
Okay, so let's take a look at some solutions to a couple of momentum problems that deal with both momentum and kinetic energy. So the first problem is question number 8. So unit 2, number 8, what we have are two blocks. One that's 2 kilogram, one that's 4 kilogram. The one that's 2 is moving to the right, 6 meters per second.
So it's interesting. I wonder if this is a voiceover. It was weird, right? Because the text showed up so quickly, but it didn't sound like there was a hitch in the audio. I'm curious if it's a voiceover.
The one that's 4 kilograms moving to the left at 4 meters per second. It's always helpful to draw a diagram. It will help you keep track of signs later and just get a ghetto sense of what's going on. So that's what we have at the beginning. And then after the collision, it says that we have the 2 and the 4 stuck together because this is a perfectly inelastic collision. And then what is the final velocity? Is it moving to the left? Is it moving to the right? We don't really know. We're going to solve the problem to figure it out. So we're looking at conservation momentum because we have no external forces acting. We just have the two blocks that are coming together. So we remember our formula, and I write it out as m2v2, meaning the mass of the 2 kilogram times the velocity of the 2 kilogram, plus the mass of the 4 times...
I'm just trying to figure out if this is a overdub or not. Because that was incredibly smooth writing, but it's timed really well. But anyways, to the problem here, let's see, to make a guess, the 4 kilograms is going to win because it's heavier and it's twice as heavy, but less than half or more than half of the speed. So this thing is going to end up going to the left. And I think we have a momentum problem. Energy is going to be not super useful here. I'm curious to see if problem number 9 has more energy stuff going on.
4 times the velocity of the 4 kilogram equals the mass of the two velocities together times, and I'm just calling it v prime, the velocity that those things are going to go with together. We're going to solve to try to find v prime. So we'll plug in our values. We got 2.
You know, that choice to do v prime for the to label the other velocity, it's clearly a totally different velocity. She can't call it v2 or v4. Calling it v24 seems weird. I mean, prime is, I'll be honest, I was like, prime, that means derivative, but probably not in this class, would be my guess. So just making it very, very clear. I loved it, right? Making it clear to her students that it's a different answer. And the way she has this written, it looks like it's kind of sort of being treated as a vector, right? We just have lefts and rights going on here. So I'm guessing she's about to make a choice, actually, as to whether right or left is positive. I mean, very likely she's going to choose right as positive. What is interesting, right, is what if you drew this at some cockamamie angle and decided to call it a two-dimensional problem, right? I mean, why would you do that, right? But there you'd have more of a vector issue going on. But yeah, so I'm going to guess that she's going to write a positive 6 and then a negative 4 here. Let's see what happens.
We got 2 kilograms and 6 meters per second. We've got 4 kilograms and a negative 4 meters per second. It's really important to remember that negative sign because that means that the block is moving to the left. This is how we're keeping track of this in terms of vectors. Now we just have some algebra to do, so we can figure out we got 12 on the left and a negative 16. So we'll add those up, and we still have the 6 kilograms times v prime. So we get negative 4 kilogram meters per second. We're going to divide that by 6 to solve and get v prime is equal to negative 0.67 meters per second. So the two blocks together will be moving to the left at about 2/3 of a meters per second. All right. Now we got to figure out the kinetic energy, the change in kinetic energy, because not only these things are we going to have a change in momentum, but we're going to have a change in energy potentially. So let's find out. So we say kinetic energy, the change is going to be the kinetic energy final minus the kinetic energy initial. Now if we remember the formula for kinetic energy, which is the energy associated with a moving mass, is called 1/2 mv squared.
I wonder if she writes it all out as fast as she possibly can and then in the overdub pauses the video, just like I've paused this video here, or does she write it out with and sort of say it out loud and think about how much time to save? This is really interesting. It's nice and clean. Takes 2 passes, and of course, 2 passes allows your brain to think twice as much. And I wonder how often she sort of says, I wish I had done it a little bit differently. But very cool. Also, this problem, right, is done. Like, we know what happens at the beginning. We know what happens at the end. Now, this question about the kinetic energy is going to be non-zero, right? It's going to say, what happened to the energy? And students really struggle with that. And I think that, where did that energy go? I'm curious to see what she has to say about that.
E squared. So we want to find the kinetic energy of each block before and then each block after, and find out what the difference is between the two. So here we go. We're going to start with the final. We go 1/2 m, we've got 6 kilograms because the 2 and the 4 are moving together, times that negative 0.67 meters per second squared.
Cool.
Now notice whenever you
The
square
negative
a
sign
negative,
doesn't matter. Yeah.
that the negative goes away. So
Yep.
really, the signs when we're doing kinetic energy don't make any difference. It's just about how fast are they going, which is really nice. You don't have to worry about signs. But you do have to remember to square the velocity term. So we square the velocity term and only the velocity term, then we multiply it by the mass in 1/2. So we get 1.35 joules. So that is the final kinetic energy. Now let's go back and figure out the initial kinetic energy. What we got is 1/2 times a 2 kilogram, and it was initially moving at 6 meters per second. And then we got the 4 kilogram, which was moving at negative 4. But again, if we square that, that negative goes away. So when we add...
So I'm really curious if there's value, and what do you guys think, right, to saying, let's see, 36 on one side versus 32 on the... So the 2 kilogram mass actually has more energy than the 4 kilogram mass, right? Oh, wow, that's interesting. Let me double check my math here. Yeah, the 2's cancel. 36 for one of them, and 16 times 2 is 32. Yeah, okay, so it's fascinating, right, that the 2 kilogram particle has more energy than the 4 kilogram particle, because in the tug of war, it sure looks like the 4 kilogram particle won, right? Because the ultimate particle ended up going left. I don't know if that's the right way as viewed in the video. So that's interesting. Does that always happen? Surely not. I wonder if there's a way to get the energies to be the same. I'm sure there is. Get the energies to be the same, but one have a higher absolute magnitude of momentum. Really cool.
If we add all that up, we're going to get 68 joules. So it started off with 68 joules of energy and ends up with only 1.35.
Wow.
So even though momentum is conserved, a lot of energy was lost. And that is
I love the sig figs here. There's none.
Collisions. When there's a collision, two things stick together, you have a lot of energy lost as heat or sound,
Yes.
but energy will be lost. So we can conclude that because the change in kinetic energy is negative, we're losing energy, we can conclude that this must be an inelastic collision, which we already knew because...
So I've got some friends who keep telling me that the sound portion is almost nothing. We should stop saying that. I actually have never done the calculation, but you can do it, right? Because we have ways to calculate the energy of sound. It's just a wave, so you just need to know the amplitude. And what you could do is say, okay, well, what if the 67 joules lost was all sound? How loud would that be, right? Could you be in the same room with it? So I am starting to wonder if sound... I mean, students get it. They're like, oh, yeah, I did hear it. Yeah, there must be some energy there. But is it a lot, right? So that's an interesting question if anyone wants to do that calculation. The heat part, it does heat up, but it's also deformations, right? So you sort of get these bonds formed. Well, it's funny when you think about forming bonds, sometimes it gives up energy, sometimes it takes energy. So I think that it's really fascinating when kinetic energy is not a useful concept and potential energy is just too hard to calculate. All of these other forms of energy are just too hard to calculate. This problem can be done with momentum alone. And of course, an elastic problem, you need both. I don't know. I've always found it fascinating that we have two ways to categorize or quantify motion. We have momentum and we have kinetic energy. It seems like one is always true and always useful. The other is sometimes true and I guess it's always true, but it's only sometimes useful. Fascinating. Let's go a little bit longer here.
Because it's stuck together, but that's what happens with the energy for this particular scenario. So let's move on. Next problem we're going to take a look at is number 9. So very similar, we have two blocks. We have a 2 kilogram block that starts moving to the right at 6 meters per second, and we have a 6 kilogram block that's not moving at all. And then after the collision, we're going to get a 2 kilogram that's moving to, well, we assume it's going to move to the left because they're going to bounce off each other. I'm guessing it's going to go left. And then we know that the 6 kilogram is moving to the right at 3 meters per second. Again, drawing these diagrams is really helpful to help us keep track of signs. And then we typically say to the right is positive, to the left is negative. So
this is a really interesting problem, and I love the way that she set it up, right? Because it almost seems like it's overspecified. Like, well, there's a collision. What's going to happen? I'm going to give you half of the answer. You just need to figure out the other half of the answer. What if you didn't give this? Could you figure out that, of course, this is going to end up being a 3? Well, subtle, right? Because if the kinetic energy is conserved, which you basically get by staring at the masses, well, it was 2 kilograms and 6 kilograms before, it's 2 kilograms and 6 kilograms after. So we can do, momentum and energy. It's really, really fascinating how complicated this gets so fast. But in this problem, one-dimensional, one mass, afterwards you know what its speed is. So this is actually a pretty straightforward momentum-only problem, though let's see if she also does the energy.
Let's go ahead and solve the momentum part of the problem.
Mm-hmm.
We're going to lay it out 2 kilograms times 6 plus 6 kilograms times 0. So that whole term is going to go away. So that's going to become 0. Is equal to 2 kilograms times v1 prime. And that's what I'm calling this velocity here, v1 prime. It's the initial velocity of the first block after the collision. That's what the prime indicates, after the collision. Plus 6 kilograms times 3 meters per second, and that's positive. So now we have to do some algebra, and we're going to solve. So we get 12 kilogram meters per second is going to be equal to 2 kilograms times that v1 prime, plus that 18 kilograms from the block on the right.
So I maybe talked over her and I wasn't sure. This actually could still be an inelastic problem, right? Because the kinetic energy might not work out. So there's only one solution if the kinetic energy works out. There's lots and lots of solutions if it doesn't, right? So I guess I was jumping to the conclusion that because it's 2 kilograms and 6 kilograms both before and after, that this is going to work out to be perfectly elastic. But now I see what she's up to. It might not be. Let's follow.
So now we're going to have to solve and isolate v1 prime, subtract 18 from both sides. I get negative 6, and then I'm going to divide that by 2, and I will get that velocity 1 prime is negative 3 kilogram meters per second. So I was right in my guess that v1 is going to be moving to the left, and it's going to be moving to the left at negative 3. Oops, that's not kilogram meters per second.
I knew she'd catch it.
Not kilogram meters per second.
I knew she'd catch that. And clearly this writing is live. Man, how does she write this well and not... I'm confused.
3 meters per second. Better. Okay, now we want to find out what is the change in kinetic energy for this scenario.
Yeah.
Again, kinetic energy, delta Ke, the change in kinetic energy is Ke final minus Ke initial. And Ke is 1/2 mv squared. So let's find the initial energy for each term and the final energy for each term and see what happens. So here we go. I'll start with Ke final. That's going to be 1/2 times that 2 kilogram times that negative 3 that we just found. We're going to square that term, plus 1/2 times 6 times 3, and square that term. And then we do the algebra, and we get that the kinetic energy final is 36 joules. Let's go ahead and find the kinetic energy at the beginning. Initial is going to be 1/2 times that 2 kilogram. The initial velocity was 6 meters per second, so we're going to square that. Plus 1/2 times 6 kilograms times 0 squared, because that thing wasn't moving. And we get 36 joules. So what we find in this problem is that the energy hasn't changed in the collision. We say that the mechanical energy is conserved. We had 36 joules to start, we had 36 joules to finish. No energy is lost, and that is a special case. And when that is true, we say that we have a perfectly elastic collision. So it's
so this is, that's kind of what I was expecting, and I was just assuming at the start, and sure enough, it turned out that was the case, right? So this problem, you wouldn't have to give the two speeds. You could say, well, I guess I know momentum and I know kinetic energy has to be conserved, and I can get both of these speeds. But it also points out, if you're in a hurry making your quizzes or tests or something, you can put any number you want here, and this first half of the problem will give you an answer. No question about it. You can put anything you want here, put 1,000 there, you'll just get something else here, and that'll be fine. But sometimes when you do this part, you'll get that energy came from somewhere, and so that there was like this additional explosion or something when they collided. I was kind of I don't know. I almost said tricked. I'm thinking about it, right? Microscopically, if this was inelastic, if there had been actually a little bit of a loss, so let's say these numbers had worked out such that the kinetic energy was a little bit of a loss. Microscopically, can they possibly still have the exact same mass? Well, it depends how microscopic you go, right? Because all energy comes from mass energy, but I'll have to think about that a little bit. So very, very cool. Loved how she did sort of an overdub, sort of a live. I'm still a little bit confused about that, but I was watching again at the bottom, the way she just churned this stuff out here was, she wasn't writing while she was talking, and yet it was clearly the whiteboard was live because she was able to erase. That was really cool. And fix it. I love the fact that she picked up her unit mistake there. That was super, super great. And I really liked how she was fixating on these vocabulary words, inelastic, elastic. Very, very cool. All right. Thanks, everybody. Have a great day. And remember, physics teachers are awesome.